Okay, I guess we can get started. Good morning and welcome to Lattice-based Cryptography II. And our first talk of this session will be given by Chenje Zhu.
Yeah. Okay. So good morning, everyone. Thanks for attending my talk and thanks for the introduction. So the main contribution of this work here is in the efficient threshold-based threshold signatures. So I will start from what is a threshold signatures. So in this setting, initially n-signers run a distributed key generation protocol to generate n secret key shares and one public key. So that by the end, each signer will hold one secret key share. And to sign a message M, require at least a threshold T of signers to be involved in order to issue a valid signature, which can be verified using the public key. And the basic security wants to guarantee that no one can forward the signature for a message if there are less than T signers are involved. So main motivation of developing threshold signature is to avoid a single point attack. They have attracted great interest in industry, for example, for crypto wallets, and there's an ongoing standardization effort by NIST. So now let's take a look at the current construction on lattice-based threshold signatures. So the early construction is based on threshold FHE. It has optimal rounds, but it's not so practical due to the use of FHE. And the follow-up work proposed a more efficient scheme is based on linear homomorphic encryptions. However, it is still relies on heavy tools such as NISIC and homomorphic trapdoor commitments. And only more recently, there has been a boom in the practical constructions and do not rely on any heavy tools. We will see a more detailed table in a minute. And before that, I would like to mention there are also other constructions that want to target stronger security, which are not the focus of this talk. So now let's take a closer look at the existing efficient constructions. So they all assume the random oracle model. And the first construction, threshold raccoon, has it's 3 rounds and it's based on standard assumptions, and with signature size about 10 kilobytes. And here, we consider 128-bit security. And it also require setting up a private key between each pair of signers. And the more recent scheme greatly improve its signature size and also avoid the needs of pairwise keys. However, it only works for small numbers of signers. And other schemes focus on better round complexity. As Patel et al. Proposed a 2-round scheme, but it's based on the non-standard assumption proposed in their paper. And in particular, this signature size is estimated based on their cryptanalysis of the new assumption. And in our prior work, we also proposed a 2-round scheme, and it's based on standard assumption and avoid the setup of a pairwise key. However, it requires a much larger signature size, in particular because it uses a special linear secret sharing scheme. And the follow-up work, Ringtail, seemed to achieve the best of both worlds. And however, the caveat here is that its concrete efficiency is estimated based on the assumption that the numbers of hash evaluation is bounded by 2 to the 60. And typically, this number should be bounded by 2 to the security parameters. And if we're plugging that, their signature size will be much larger. So we can see that all existing 2-round schemes here have some caveats. So the key question is, could we get a 2-round scheme that is secure on the standard assumptions with comparable signature size without any heuristic? And we gave affirmative answer in this work. And our main result shows that surprisingly, this non-standard assumption is actually implied by the standard assumption. And this implies that the EKT scheme is secure on the standard assumption. And based on our security analysis, the estimated signature size is about 30 kilobytes. It is worse than the cryptanalysis-based parameters, but it's still in the same ballpark. And based on the techniques, we also show, we also provide a tighter security for our prior scheme and resulting much better efficiency. And we note that here the advantage of CAS is that it has a simpler setup. So an overview of this work as follows. So we first propose a modification of the AOM MWE problem, referred to as AOM MISIS. So this is a no harder variant, which means that the hardness of our problem implies the hardness of theirs. And then we show that the hardness of our problems is implied by the standard assumptions. And further, we give a direct reduction from the hardness of alpha assumption to the security of the EKT, and it's tighter than going through the AOM MWE route. And also, we find the security of CAT scheme can also be based on the hardness of a problem, and this will give a much better parameters. So for the rest of talk, I will tell you what is this AOM MI6 problem and explain some idea behind our reduction. So first, let's recall the short integer solution problem. So here, the adversary is given a random matrix, and the goal is to output a non-zero short solution such that the A times X is equal to 0 mod Q. This problem is conjectured to be hard even for quantum adversary A for certain parameters. And when we add M in front, we refer to the modular version of the assumption, where the integer space is replaced with a polynomial ring. And for practical scheme, we usually use the modular version for better efficiency. But for simplicity of this talk, I will only focus on the integer lattices. And ISIS refers to the inhomogeneous version of cis, where the only difference is that now the goal is changed to find a short solution for random target Y. Now let's first see what is a one more ISIS problem. So here the adversary is given L ISIS challenges, and the goal is to output a short solution for each challenge. And here we use convenient notation B star to denote a set of all the vectors that is non-zero and is short. And in addition, A has access to a pre-image oracle, which takes an arbitrary target vector and outputs a pre-image as sample from this Gaussian distribution. To make this problem non-trivial, we also require that the numbers of PI queries is bounded is less than L. In other words, the adversary have to solve at least one more challenges than the numbers of PI queries. And hence name one more. And finally, let's see how the algebraic one more problem is defined. So similar to before, the adversary still need to solve the L challenges, but the difference is now the challenge is sampled with small pre-image. It means that the challenger will first sample a short xi and compute yi as A times xi. And moreover, now the PI oracle also becomes weaker in a sense that the adversary could only ask for a pre-image of a linear combination of the challenge. So hence the name algebraic. And so in particular, the PI oracle will take a coefficient vector and output the sum of Ti times Xi. And so this is actually a pre-image of the sum of Ti times Yi. And similarly, we require that the numbers of PI queries is less than L. However, the prior work pointed out that even under this condition, the problem is still easy to solve. It means that we need to add actual condition on these PI queries. And in particular, in this work, the condition is as follows. So we additionally require that exists a short vector U such that it is orthogonal to all the PI queries. So here the TJ denotes the J's PI query. And I also want to mention that the AOM MWE problem, proposing the prior work, is essentially the same problem. The only difference is what constraint we put on the queries. And we call it AOM MI6 because we think it's closer to I6 problem where they think it's closer to MWE. Yeah. So now let's take a closer look at our constraint. So one way to understand it is that it implies the entropy of all the Xi's remains high even after you're seeing all the PI responses. To see this, let's consider the lattice defined for a certain Xi's. So we can show that all the points on these lattices result in the same PI response. So this means if U is small, then the lattice will kind of dense. So all the points, so the Gaussian distribution condition on these lattices will have high entropy. And to see that all the pointed lattices have the same PI response, you can just take any point on these lattices and compute this PI response and expand it. We find the second term will vanish because this U is orthogonal to the TJ. So they were equal to the PI response computed based on xi. And now let's see a few examples of these valid queries. So in the first example, TI queries is just L minus 1 unit vectors. Then the corresponding U would be the unit vector that's orthogonal to all the other queries. And in the second example, all the PI queries are just uniformly sampled. And for here, the U would be a cis solution for the matrix T that is formed by all these queries. And if K is sufficiently small, we know there will be high probability that such a U exists. So now we'll focus on the reduction from the standard assumptions. So first, I will give a rough picture of the theorem we prove here. So here recall that beta U denotes the norm of this short vector U. And this delta alpha is a constant depending on the alpha. And cis and LW arrow are roughly as follows. So please check up a paper if you want the exact theorem. So one thing I want to highlight here is that how the hardness of the AOM and my cis depends on the beta U. In particular, for smaller beta U, it will result in a larger LW arrow, which means the problem is harder. And now I'll explain the reduction from the cis to the one more problem. So the reduction idea is actually from our prior work, but in the D-log setting, where we show some one more type assumption is also implied by the D-log assumption. So reduction is actually quite simple. So here, let's consider anniversary B for the cis problem, anniversary A for the one more problem. And for simplicity, let's assume that A always wins. So initially, B, after receiving this random matrix A, I just run the A with a matrix and also L challenges sampled by itself. And then since the Xi is sampled by B, the B can just answer the A's queries honestly. And after that, after A returns all the solutions, if B can find some Zi that is not equal to Xi, then B just outputs Zi minus Xi. So it's not hard to see that this Zi minus Xi would be a valid cis solution, because first we know A times Zi is equal to Yi is equal to A times Xi mod Q. So therefore, we have the A times Zi minus Xi would be 0 mod Q. And also, this vector is short because both Zi and Xi is short. So the only problem left here is how we can show exists such a Zi that is not equal to Xi. So the intuition here that this hold is because all the information that A received is not enough for A to recover all the Xi. In other words, that the entropy of X remains high given all the challenges and all the PI response. To see this more concretely, let's consider two randomness and two executions, where the first one is use the Xi and the second one uses Xi prime. So, and suppose that in these two executions, we have all the challenges are the same and all the PI queries are the same. Then the A will output the same solutions, assuming A is deterministic without loss of generality. And then you see, since there exists an Xi that's not equal to Xi prime, we know either Zi is not equal to Xi or Zi is not equal to Xi prime. So this means that in at least one of the world, B will wins. So then the question boils down to how we can find an Xi prime such that two conditions holds. So for the first condition, the idea is that there exists a short delta such that the A times delta is equal to 0 mod Q. So therefore, for any Xi, if it plus any K times delta, it will give you the same challenge as Xi. And for the second condition, this is exactly what we discussed before. So because of the existence of U, we know there is a lattice of a point that have the same PI queries, have the same PI response. So in particular, we have if we plus Xi, by the UI times a vector, it will give you the same PI responses. Combining these two, we can define the xi in the following way, and this will satisfy both conditions. And there was still some actual work to prove the theorem, but I will not go through that. So the only thing I want to say is that to make the theorem go through, we require both the U and delta to have small norm. And the last thing I want to mention is that we use the LWE here to embed a shorter solution to A to improve the tightness of the bound. And to conclude, in this work, we pose a new one more type problem. We show its hardness is implied by the standard assumption, and its hardness also implies the security of two existing threshold signature scheme. And for the open problem, so it's interesting to see whether we can extend our result to other distributions of xi's. For example, if xi is sampled from a bounded uniform distribution, could we get a similar reduction? And the second is, as I mentioned, there's a gap between the cryptanalysis and reduction. Could we close that gap? And yeah, that's all I want to talk about. And thank you for listening. And here's a link to the paper.
We have time for questions. I guess while we're waiting for other people to come down to the microphone, I'm curious to hear more details about the gap between the cryptanalysis and reduction. I guess you had concrete parameters, but I'm also, what does that look like?
So yeah, I think so concrete bound here is like I showed a theorem, but I made some parameters like there was square root of n factors there, and that will actually have a fact if you want to compute the concrete parameters. So it's interesting to see whether we can remove those those factors there.
And if you concretely instantiate the scheme with concrete parameters, like what does that look like? Or did you do that?
Sorry, what do you mean?
So if you concretely instantiate your signature scheme with the concrete parameters,
Yeah.
like what do the parameters look like?
Oh, I mentioned it was for the EKT scheme is about 30 kilobytes for the signature size. I don't remember for the communication, but it's roughly like a 2 times of the origin or 3 times of the origin.
2 or 3 times? Cool.
Yeah.
Hi, thank you for the great talk. You kind of mentioned that the adversary can be assumed to be deterministic at some point. And if it's a quantum adversary, then you can't really assume that, right? Can you kind of elaborate on that?
Yeah, that's a good question. I haven't thought much about it. Yeah, I'm not sure. I think for lattice, it might be like more problems on that. Yeah.
Yeah.
Then can you kind of like explain to us where you needed this assumption in the proof? Like which step did you require the adversary to be deterministic?
Oh, you mean A to be deterministic? Yeah, actually, I think if you don't have deterministic, you just yeah, I think you can just have some randomness there, and you fix the randomness, and you just make the proof works for any randomness. Yeah, I don't think there's an obstacle to prove if A is not deterministic.
Great, thank you.
Yeah, thanks.
Well, let's thank the speaker. Yeah.
Forward, backward, laser.
Our next talk is on Gaussian sampling for QRA lattices and linear codes with Lee weight, and the talk will be given by Maya Lee.
Good morning. Thank you for coming to my talk and thank you for the introduction. So I'll be talking about lattice Gaussian sampling and in particular our work to obtain a simple and efficient sampler for certain QRA lattices using techniques from coding theory. And this work was done in collaboration with my co-author Mayara from the University of Tartu and my supervisor Tsong from Imperial College London. So sampling in cryptography, why do we care? Well, it's well known that in deterministic protocols, we can't use them securely more than once, so we need to inject some sort of randomness somehow, and sampling helps us to achieve this. So it's no surprise that sampling is an important subroutine for many different kinds of protocols. For example, the lit-based signature scheme HAWK uses sampling directly to output a signature. So to sign a message, you take your message, you hash it to some target vector T, and then you sample from a distribution centered on the target to get a lattice vector, which is somewhat close to that target, and that's your signature that you output. Other than that, sampling is also important in a lot of worst to average case reductions for hard problems, such as shortest or closest vector problem. And theoretically, we can even use sampling to solve these problems directly. So as for what distribution we use, we often typically choose Gaussian distributions. And since lattices are discrete additive subgroups of Rn, we use discrete Gaussian distributions as defined here. So in our work, we are mainly concerned with two aspects of this distribution. The first is this denominator here, and the second is this sampling width, or you may just call it width S, which controls the shape of our distribution. So we'll first take a look at this sampling width, and then we'll return to this denominator later. So in cryptography, we always have at least two main goals, security and efficiency, and whatever sampling method we use, we have to make sure that it adheres to these two things. And how we try to balance these two goals, well, we have something called the smoothing parameter, which tells us how these two things kind of interact in sampling. And the smoothing parameter is the minimum amount of noise that we add to the lattice to make the distribution appear uniform. So it's the smallest ball that we add to each lattice point so that we are kind of like smoothing this region into like one uniform darkness color. Mathematically, the smoothing parameter can be computed using the theta series of the dual lattice, which is something that we'll see in a few slides' time. But let's first consider what happens when we sample sufficiently above smoothing. So if we're sufficiently above smoothing, then our S is bigger, our distribution looks flatter, and in other good news, we generally know how to sample efficiently in this regime. On the other hand, you may have heard in some talks yesterday that we have better security guarantees when we have a smaller sampling width. So much of the previous work kind of lives in this blue region where we're sufficiently above smoothing. So the Klein and GPV sampler, Piker's perturbation sampler, they all work for arbitrary lattices when our sampling width is big enough. 2 years ago at Asia Crypt 2023, Espitao, Wale, and Yu published a sampler leveraging lattice filtrations, which improved a lot on the sampling width, so you could sample much closer to smoothing, especially for certain root lattices. And this idea was kind of used as well by my supervisor for a specific set of binary construction A lattices. But actually, Campello and Belfiore, they improved upon this further for binary construction A lattices, and they proved that there was a method of sampling where you could flexibly choose your sampling width. So you could choose it to be at smoothing. And notice that all of the previous samplers, they kind of live on this side of the diagram, and there's a reason for that. The reason being that once you go below smoothing, you actually start to leak some secret information about your lattice. So we don't ever want to sample below smoothing. So our ideal situation is to sample at smoothing or close to smoothing. And this is what our work tries to do. We try to kind of bridge this gap from sufficiently above to closer, as close as possible to smoothing as we can for certain Q-array lattices. So Q-array lattices or construction A lattices are in bijection with codes over the ring ZQ. And this is nice because it allows us to kind of express the lattice in the so-called code formula. So that's where this like construction A name comes from. And it allows us to look at a finite cut of the lattice rather than the whole thing. And because of this connection to linear codes, we can evaluate some of the properties of the lattice more easily via the associated code. So one of these properties that we can evaluate is something called the theta series of the lattice, which I mentioned a few slides ago. And the theta series of a lattice records the number of lattice vectors of each norm. In coding theory, we have something similar in the form of a weight enumerator. In this case, we're going to use a weight called the Lie weight as defined here. And you can see from the definition that the Lie weight for any given Q has this really nice symmetry about it. So if we take Q equal to 4, for example, 1 and 3 are going to have the same Lie weight as each other because the minimum of 1 and 3 is the same as the minimum of 3 and 1. So we can take a code word and we can look at how many coordinates in the code word have each Lie weight. And we're going to call this the Lie weight profile of that word. And then our weight enumerator, which we call the symmetrized weight enumerator, basically does what the theta series does for a lattice. It records the number of code words of each Lie weight profile. But why do we care about theta series? I mean, we're talking about sampling. If you recall the denominator from the first few slides, if we rewrite this expression by setting z equal to I over s squared, where s is our sampling width, we can actually re-express this as the theta series of the lattice, where we're parametrized by z. And this means that the geometric information that's captured by the theta series is exactly what we want to define our sampling probabilities. So this kind of becomes our first tool in our sampling method, the theta series. So we can show for Q-array lattices that the theta series is exactly given by the symmetrized weight enumerator of the associated code. And this helps us in our paper to come to this next key observation that sampling a Q-array lattice is essentially equivalent to sampling a code word in its associated code with respect to the Lie weight profile. So how do we see that connection between the theta series and the symmetrized weight enumerator? I'll do a really short example with Q equals 4 again. So we consider a coset defined by some code word, same code word as before. And then we'll analyze what all the possible entries of a coordinate in a vector in this coset can look like. And for each of these cases, we can derive a one-dimensional theta series. And using some theta series identities, we can see that there's, again, this nice symmetry, which is exactly captured by the Lie weight. So 4z plus 1 is going to have the same theta series as 4z plus 3. Then we can go back to our coset and use this trick of breaking it into an isometric direct sum. And isometry preserves lattice norms, so it preserves theta series. And then for each part of the direct sum, we use the one-dimensional theta series that we obtained earlier. And you'll notice that the exponents of the theta series here are exactly going to be the entries of your Lie weight profile. So the code word that's there has a Lie weight profile of 1, 4, 2. And this kind of hints at our second tool, which is using these cosets. So the idea with coset decomposition is we have our lattice lambda, and we express it as a disjoint union of its cosets. And then we have a very nice generic sampling method that we can use from this. So we first sample a coset representative. In this case, it'll be from the code. And then we can sample a lattice vector from the pre-selected coset. So how we use this for construction A is very straightforward. Because we can write the lattice as QZN plus some code, our lambda prime is going to be QZN, and our set of coset representatives is our code, or potentially a shifted code. So the first step, we sample a coset representative from the associated code, and this probability depends only on the Lie weight profile, which we know because of our theta series analysis. And then we use, again, this trick of decomposing into direct sum to sample our vector from the coset. So we can do this by sampling each individual part of the vector using Z samplers, and this is very efficient. So the nice thing about our method is that none of these steps really depend on our choice of sampling width. So we can sample flexibly, just like Campello and Belfiore, and that means we could choose to sample at smoothing. However, we still have the second goal of efficiency in mind. And while step 2 is efficient and we know how to do, step 1 is really like where the bottleneck is created. Because since sampling QRA lattices is equivalent to sampling code words, and we know sampling code words is quite a difficult problem, we kind of have an issue here. Luckily, in our paper, we give some tricks to ensure that in some cases you can have an efficient sampler. So one of these tricks is to use the structure, like the code, basically. So we can look at the code and try to use some information about it. For example, the symmetry of the code. So if Q is equal to 2, we're in the binary construction A case. And if we have a code that contains the all ones vector, then our code is said to be symmetric. And that means that we can recover our entire code from just half of it. So an example of this is the E8 lattice, which we can construct from the Reed-Muller code. And you can see from the weight enumerator here that it's symmetric. So we don't need to store the entire code in order to sample. We can store half of it and then recover the rest of the code words from there. Another trick to use is just to use like general code structure. So again, for example, with E8, you can notice from the weight enumerator that most of the non-trivial code words, so all the code words except for 0 and 1, are weight 4 words. So if you need to sample a weight 4 word, you can do so with very high probability. You can use rejection sampling with just like 2 iterations, basically. Another example in which this is even more useful is the DN lattices. So these are constructed from the parity check code, which contains all the code words of even weight. And so to sample here, we don't even need to store the parity check code. You can sample an even weight. This probability will depend on the Lie weight profiles. But then once you've sampled that even weight, all you need to do is uniformly choose that number of non-zero coordinates, and that's a code word in the code. Another trick that we use often in the paper is trying to break things into smaller steps to do things more easily. So when Q is a power of 2, there are some conditions under which we may find a binary decomposition of a code over a big ring Z to the Z2L. So in this case, if you can find these codes where these CI are actually codes over F2, then what we do is you sample first from one level, and then in the next level, you will compute a conditional probability of selecting the next code word based on the fact that you've already pre-selected one in the previous step. And this is helpful because C might be a really big code over a bigger ring, and it's sometimes easier to deal with binary codes. So by breaking it down into these smaller steps, we're actually like reducing the search space and the number of Lie weight profiles that we have to compute. And to actually compute these Lie weight profiles, we borrow another technique from coding theory called the Schur product. So you can use the Schur product to define a linear system of equations that allows you to solve for what your Lie weight profile should look like. So where our work fits in with all the previous work is where Campello and Belfior's work was previously. So we extend their methods for more general Q, more than 2. And because our methods don't depend on the sampling width, we can choose to sample exactly at smoothing. Another nice thing that I should mention is that because we have this really nice characterization of the theta series, we can calculate the smoothing parameter for a lot of these lattices exactly. So we compared our work with the lattice filtration sampler from 2023. And not only can we sample closer to smoothing than their provided estimates, which to be fair, were very good estimates, but we can also do so a lot faster in many cases. So the work that really remains for the future is obviously we focus on a very specific family of lattices, and sampling close to smoothing for arbitrary lattices is still an open problem. And it would also be interesting to see how improvements in coding theory and coding techniques may help us improve the efficiency of our samplers. So that's all that I really wanted to say, and I'm happy to take questions. And if you want to talk offline, I'm here for the rest of the conference, and my co-author is as well.
Thank you very much for the talk. Maybe this is a bit of a weird question, but I've noticed that one of your co-author, Kongling, also has papers giving methods to sample vectors in lattices that aren't Curie lattices. Do you think what you just presented could be adapted to that kind of case, or is that not relevant?
So our methods can be slightly more generalized in the sense of the coset decomposition idea. So if you, for example, A2 is not a Q-area lattice, but it has a very nice coset decomposition. So we can use this trick, but it might be difficult to find lattices with this nice coset decomposition. Does that answer your question?
Yes, thank you very much.
I have a question. So it seems like there's you're taking advantage of a lot of structure in these lattices, and for a lot of the cryptographic lattices, we want to not have structure. Is there any hope in that case, or?
Yeah, so I guess this is always kind of the double-edged sword of having structure, is that it may help on the efficiency part, but of course, it may also help someone to attack schemes built from these lattices more easily. So at the moment, we're not sure how to make our methods efficient without utilizing some structure of the code. So that's kind of an open challenge for us.
Hi, thanks for the nice talk. I was wondering, how do you get like exact sampling or closeness, and what closeness measure do you use?
So we get exact sampling. That's because wrong direction. Because of this coset, decomposition sampler, the final output probability is exactly like the one defined by the Gaussian distribution.
Yes. Thank you.
There are no more questions. I guess we can thank the speaker again. So our next talk is assessing the impact of a variant of Matsov's dual attack on Kyber, and the talk will be given by Kevin Carrier.
Good morning, everyone, and thank you for the introduction. So I will talk about dual lattice attacks on the LWE problem in this presentation, and it's a work in collaboration with Charles Meyer-Heninger, Yixin Chen, and Jean-Pierre Tillich from INRIAD Paris and Rennes. So let me start with a short introduction to introduce the problem of LWE and what are dual attacks. So the learning with error problem can be stated as follows. So let the public matrix A over ZQ and two secret vector S and E over ZQ2, and let a vector B equals to A times S plus E. One wants to, given A and B, recover the secret vector S. And in what follows, what I will call the plain LWE problem is when the secret vector S will be drawn uniformly at random from ZQ to the N, and E is a short vector. And what I will call the small LWE problem, it's when S and E are both short. So mainly we will focus on this second problem because it's a problem that interested us for Kyber. So let's talk about dual attacks, and in particular first on Guo and Johnson's dual attacks that they presented at AsiaCrypt in 2021. So to explain Guo and Johnson's dual attacks, let's first reformulate the small LWE problem as follows. So we define from the matrix A a new matrix B from the construction A on the matrix A. And defining this matrix B and the vectors X and Y, we can reformulate the small LWE problem by given the matrix B and the vector Y, find the vector X on the lattice generated by the basis B, such that X is close to Y. So that problem is exactly the same problem that the small LWE problem. And so the Guo and Johnson algorithm proceed as follows. So first they partition the lattice into sparser lattices, sublattices, so that we denote lambda 1 to lambda n. And Guo and Johnson algorithms trying to find the sublattice lambda I that is closest to Y, and that probably contains the vector X. So to do that, they define a score function based on dual short vectors. So the set S of short vectors on the dual of the lattice generated by B. And this score function had the property that for the wanted lambda I, we have a score which is maximum. And to find the desired sublattice, we only have to proceed to an exhaustive search that we can actually accelerate using fast Fourier transform. So when we find these sublattices, one only has to solve the sub-LWE problem, the sub-LWE problem. That is easier because the lattice involved in this sub-LWE problem is sparser. So that's the idea behind the Guo and Johnson's dual attacks. But the problem is there is a controversy about dual attacks, and in particular about Guo and Johnson dual attacks, because their analysis is based on an independence assumption that says the vectors in S, so the short vector in the dual space, are assumed to be independent. But at Crypto 2023, Duca and Pulse show that the independence assumption actually generally does not hold. And so because of that, many false positive can appear. And it's the case actually in the Guo and Johnson's dual attacks that makes it does not work. And the authors show that it's probably the same situation for Matsov, which is more advanced dual attacks. In two recent papers, a new approach was proposed to analyze dual attacks, which does not use the independence assumption, and it was we will use in the rest of the presentation. So our contribution in our paper are multiple. First, we propose a variant of Matsov's dual attacks based on coding theory in particular based on lossy source coding, and in particular on polar code, which are particularly efficient for lossy source coding. We propose also a rigorous analysis of our algorithm that is not rely on the independence assumption, so using the same approach that I mentioned before. And we apply our algorithm to Kyber, a recently standardized public key encryption scheme. And our results show that the security level of Kyber might be slightly under the NIST requirement. And in particular, we show that even if the complexity claimed by Microsoft is false, we can actually, with our variant of dual attacks, be able to achieve some results that are quite close to those of Microsoft. So let me give more details about our variants of Microsoft dual attacks. Let's recall the equality behind the LWE problem, which is B equal to A times S plus E. So first, up to a permutation, we divide the matrix A into three submatrices, A NU, A LSC, and A LAT. And using the A LAT part, we build the matrix B LAT, which is a construction A of A LAT transpose. And we also divide the secret vector accordingly. Then we apply a short vector sampler on the lattice generated by BLAT to find many short vectors in the lattice generated by BLAT. By doing this, we actually find many short pairs XY, such that Y is equals to A lat transpose times X. And so now, since B is equals to AS plus E, and if we apply scalar product by X on the two members of this equality, and if we rearrange the term, we obtain the following equation, where the green part are the things that we know, and the red part are the things that we don't know. And what is interesting in this equation is that first, the two last terms of this equation are biased towards zero. Why? Because the vectors Y, S lat, X, and E are all shorts. So these two scalar products are biased towards zero, or likely to be zero. Another point in our variant is that we will make the bet that SNU is equal to zero. So in the rest of the presentation, I will consider that I know SNU has the vector 0. And so here we are faced to a sample which looks like a LWE sample, a new LWE sample. And actually, this equation, we have multiple versions of this equation because we have multiple pairs X and Y that we can apply. So what we've done is we've reduced the first small LWE problem, the original LWE problem, to another small LWE problem. And so we will denote the parameter of this new LWE problem by A prime, S prime, E prime, and B prime. So only by concatenating the equation above. And rewriting the equation gives the following equation, which is a LWE sample. And now to solve this new small LWE problem, one only has to make an exhaustive search to find the secret vector S prime that we can actually accelerate using a fast Fourier transform. So the search is made on the search space ZQ to the NLC, where live S prime. But by doing an exhaustive search on this space, we does not actually exploit the fact that S prime is short. And so to exploit this point, we can reduce the new small LWE problem to a plain LWE problem. And there is two strategies for that. The strategy of Matsoff consists in reducing the modulus Q. So we reduce the research space drastically. For instance, in Kyber, Q is something like 3,000. And with modulus switching, they reduce to a space over Z5. And in our paper, we propose another solution, which is to reduce instead the dimension of the space. So to reduce NLSC using lossy source coding, so using a lossy compression. A first result of our paper is that our coding approach is actually asymptotically better than modulus switching. Now, we can give more details about this coding approach. So first, we define a polar code. Why a polar code? It's because it's a particular efficient code for lossy source code. So generated by a certain matrix J of dimension KLSC and length NLSC. And then we apply an efficient decoding algorithm on each rows of A prime. So we produce with that the matrix U and ELSC such that A prime is equals to UJ plus ELSC. So in this equation, A prime, each rows of A prime are the word to decode, and each rows of UJ are the code word that we decode, and each rows of ELSC is an error vector. So each rows of ELSC is short. And so rewriting the equation above using this equality, we obtain this new LWE sample where this time our secret is no more S prime but GS prime. So that is actually a compressed version of S prime. And so what we've done is actually reduce the small LWE problem to a plain LWE problem. So here, the new secret is GS prime, and so is of smaller dimension. But if we apply a perfect compression operation, that means GS prime is no more small, is no more short, but random. So now to solve the plain LWE problem, we use the same techniques as in Guo and Johnson. That means we use fast Fourier transform. So to do that, we need to define a score function that we can compute using an FFT. Here I give you our score function in a simplified version. In this equation, the function f is simply a function which is such that it returns something that is close to 0 when we make the good guess. That means when SNU and SLSC, those two parts of the vector, are actually equal to 0 and z. And f returns something random in ZQ if we make the wrong guess. And the set W, where we do the sum is actually made of the short vector sampled in the dual lattice and the word decoded by our polar codes. And so defining our score function like this, we have some properties on this score function. Essentially, when we make the good guess, we have that EW is large, and when we make the wrong guess, because of the properties of f, we have that EW is close to 0. So now it remains to find a threshold for which, when we are below this threshold, we consider that EW is close to 0, and when we are above this threshold, we consider that EW is large. So we need to understand perfectly the distribution of our score function. But because this score function is defined by a sum, we can simply use the central limit theorem and just have to understand the distribution of each term of the sum. But we cannot do that because it's suppose that each term are independent, and that is exactly the independent assumption that have proved to be false. So we need to find another techniques to drop the independence assumption. And without going too much into the details, the idea of the new approach to analyze dual attacks consists in have a dual vision of the score function by applying the Poisson summation formula that reduce the analysis of our score function to the analysis of the length enumerator of a coset of a particular lattice that you can perfectly define. Here we have to determine the distribution of Nij. So we know the lattice, and we know also the translation vector that defines the coset. We know in particular that T is short if we make the good guess, and T is random if otherwise. And so we have techniques to distinguish a good guess from a wrong guess, because when we make the good guess, we have that the coset contains a particular short vector, which is T, because the lattice contains 0, so the coset contains T, which is particularly short. And when we make the wrong guess, then we have a coset which is actually a random coset of a random lattice. And so to count the number of false positives, one only has to count the number of particular short vectors in a random coset. So to conclude this presentation, I will answer some questions around around dual lattice attacks. First, we answered the question asked by Duca and Pulse in the Crypto 2023, which was, does dual lattice attack even works? And our answer to this question is actually yes. In particular, does Matsov works? It's more complicated to answer this question because the parameter of Matsov does not work, but probably we can correct the parameters, find some new parameters for which Matsov works. And even if it does not, we show that we were able to approach their results with our variant of Matsov. And also, I present you some result on Kyber in my introduction. And so a question that we can ask is the security of Kyber being challenged? And the actual response to this question, it's not really, even if I said that the security of Kyber is probably a bit lower, the NIST requirement, because actually our computational model is quite simplistic. And so probably if we make some more precise computation, for instance, if we consider a more precise model, access memory model, probably that we will be closer to the NIST requirement. But to counterbalance this point, we have to remark that the dual attacks that we propose is quite simple because it was just to confirm that it can work, but we can do many improvements on dual attacks that I list here in this slide. Thank you for your attention, and I'm open to your question if you have some.
So the parameters of Kyber are too large to test this experimentally. Did you try to support your analysis with any kind of experiments on smaller parameters?
Yeah. So first, there is several experiments that we've done. First, for polar codes. To prove that polar codes are well suited for our work. And for polar code, we use the actual length for Kyber. So we don't use a smaller parameter. So that works perfectly. And we also prove our analysis by a simulation on small parameters that tends to show that our analysis is correct.
How large were the parameters?
Not so large, actually. I think something like 10% the parameter of Kyber.
And did you try to implement Matsov's technique?
No, but it probably be the next step, yeah.
Thanks.
Yeah.
Thank you very much for the talk. I have a quick question. I think maybe I missed it, but I think in your presentation you don't mention the need to sample short vectors in kind of a dual lattice in order to distinguish between your good and bad guess. Is this not mentioned because you don't need it, or is it not mentioned to keep this simple?
I'm not sure to understand the question, but about the short vector sampler?
Yeah,
short vector sampler we used?
The question was more like, do you need one, or like?
I need a short vector sampler. That I didn't mention which short vector sampler I use. We use the same as in Matsov, and actually there is lots of problem with their short vector sampler. And it's one of the improvements that we can do, use a better short vector sampler. I didn't mention which one we use, but yeah, we use one.
Okay, thank you.
It's details on the paper.
Are there any, final questions?
I just have a quick question. So when you try to reduce the dimension, what is the strategy to choose the dimension? You reduce the matrix A into a submatrix, right? So how you choose the dimensions?
Sorry, I don't know.
So you try to divide the matrix A into a submatrix to
Yeah.
reduce the dimension. So how can you choose the dimensions?
The submatrix? How we
The submatrix A in the beginning of the top?
to reduce the dimension,
Yeah.
we use the matrix J.
Can you go to the first slide when you try to? Yeah, how this one, the next one. So how can you decide the dimension for n?
The dimension for NLSC is we use some numerical optimization.
Okay.
To determine that dimension. And actually the dimension, another of the dimension here, nlat is very big, and NNU is very small, between 1 and 10, and NLSC is something like 40, and nlat something like 500.
Okay, thank you.
But we use numerical methods.
Let's thank the speaker again.
Thank you.
Our final talk will be online.
Sorry, a quick announcement. There's a broken pane of glass above the entrance exit vestibule on this side. So when you do exit after the talk, please use that entrance exit. We're asked to not use this just for safety to make sure everybody's okay. Thank you.
Hello everyone, my name is Corentin Jeudi, and today I want to present a joint work with Olivier Sanders on a new post-quantum blind signatures on lattices from a technique we call entropy recycling, which I'm going to get to in the presentation. But first, a little bit of background starting from signatures. In a regular signature scheme, we have two workflows, the issuance phase and the authentication phase. In the issuance, the user sends the message they want certified by the signer and receives a signature that only the signer can produce. Then they can give out the signature and the message it certifies to authenticate to verifiers. The problem with this blueprint is that it is not suited for certain privacy-enhanced applications. We can indeed see that it is possible to trace back the authentication phase to the corresponding issuance that emitted the signature because both the message and the signature are revealed. And this is undesirable in a number of applications, like, for example, untraceable payments or eCash systems. And this is why David Schoen proposed in '82 the notion of blind signature, which addresses this traceability issue. For that, it requires a property called blindness, which specifically states that the adversary cannot trace back a signature from its issuance, which also means the message cannot be revealed in both protocols simultaneously. Now, because of these constraints on the message, we must then overhaul the standard notion of unforgeability, which is why we use one more unforgeability instead to simply ensure that an adversary cannot produce more valid blind signatures than they received from the legitimate signer. One framework to construct blind signatures is as follows. Instead of sending the message in clear, the user will hide it using cryptographic building blocks like a cryptographic commitment scheme, for example. Then the signer produces a partial signature on this commitment. And after that, the user uses a complete mechanism that produces the final blind signature, but in such a way that it is unlinkable to the partial signature. And this is very important for blindness, and it usually makes use, in some cases, of zero-knowledge proofs, for example. Then the user can send the message and the blind signature without breaking blindness because the message was hidden in the issuance and the partial and final signatures are unlinkable. Now, this blueprint has been used in prior constructions, even in a post-quantum setting, but a recent project called Project Tourbillon from the BIS Innovation Hub and the Swiss National Bank still concluded that further research was needed for deploying post-quantum eCash and therefore post-quantum blind signatures. And this is one of the motivations behind our work. Okay, so before I get into the details of our constructions, let me give a few background notions that we will need. First, our security relies on well-known lattice assumptions such as ISIS and LWE. The ISIS problem gives a uniform matrix A and a uniform syndrome U and asks to find a short X such that AX equals U mod Q. Now, when U equals to 0, we have the homogeneous version of that, the SIS problem, which further constrains X to be non-zero so that the problem is non-trivial. And we can also define LWE as a decision version of ISIS, where the goal is to distinguish between a vector of the form AX mod Q for random short X from a perfectly random vector U. Okay, so these problems represent our security foundation, and they are believed to be hard, unless one knows a trapdoor on the matrix A. There are several families of trapdoors, but in our case, we rely on the gadget-based trapdoors of Michanchoy and Peikert because they lead to signatures that smoothly interact with zero-knowledge proofs, which we will need for blindness. These matrices are of the form A sub t, where the first block A equals the identity and a uniform A prime, and the second block is Tg minus A times R. R is a short matrix, which is our trapdoor, and the product A times R can actually be made public under ISIS and LWE. Then T is called the tag that we will need for the security proof, and G is the gadget matrix, which is basically the base B recomposition matrix. And associated to those matrices, we have a pre-image sampler, which solves ISIS on the matrix A sub T using the trapdoor, basically. It allows to sample short random V's such that A sub T times V equals U for any syndrome U that we want, and that without leaking our secret trapdoor R. I also need a high-level understanding of lattice-based zero knowledge, and for that we will use the now famous LNP framework from Crypto 2022. In a nutshell, it allows to prove quadratic equations mod Q, like proving knowledge of a tag and a preimage of U for A sub T, or proving norm constraints mod Q, that is, W inner product with itself equals to B squared mod Q. And the framework then lifts those norm equations over the integers as long as Q is somewhat larger than B squared, so that there is no wraparound mod Q and the equation actually holds over the integers. Then the proof itself contains many elements, including a masked opening of the witness, which is typical for Schnorr-like proofs, where here Y is the mask and C is the challenge. And it means that the proof size linearly depends on the dimension of the witness. The proof also contains many other elements like commitments, alpha-1 coefficient masks, which are all uniform looking mod Q. So the proof size also depends on how big Q is. So if you need to keep one thing in mind from this slide, it is that to reach smaller proof sizes, we want a smaller witness dimension or smaller modulus. These are the two main avenues we will explore to improve the blind signature size. All right, now let's see how to construct blind signatures from gadget trapdoors. We start by hiding the message in an ITI commitment CR plus DM, where R is a short randomness used to hide the message part. And for the security proof, we also need to use a so-called encryption to the sky of the message. And the latter is basically a public key encryption of the message where no one knows the decryption key. And this can be enforced by generating the public key using a hash function like modeled as a random oracle. And after that, we then prove at zero knowledge that all of this is well formed, so that the signer does not sign any random garbage. So we basically have a verifiable commitment and verifiable encryption here. Then the signer verifies the proof to make sure everything's okay before continuing. It then generates a tag and uses the gadget-based sampler to find a preimage of U plus the commitment, which it sends back as the partial signature. And the user then verifies the validity of this partial signature and then generates a proof of this verification algorithm, essentially. So the final blind signature is a proof of T, V, and R such that the equation below is verified, that T is in the correct check space, and that V and R are small in norm. And there you have a blind signature scheme. But so far, nothing is actually super new. This framework has already been used in the state of the art, albeit with a few changes, like the use of Falcon instead of gadget trapdoors, for example, etc., etc. So we will now see how we can leverage gadget trapdoors and other ideas like our entropy recycling technique to optimize this approach further. First, we notice that the final proof needs to include R, the commitment randomness, within the witness, which increases the witness dimension and thus the proof size. So this is where gadget trapdoors become useful because we can actually reuse the first part of A sub T as the commitment matrix, while keeping a hiding commitment as it contains a perfectly uniform matrix A prime. Then what this allows us to do is to essentially merge the commitment randomness R to the top part of V to reduce the final witness dimension. So how does it work? Well, we simply reuse A in the commitment phase instead of an uncorrelated matrix C. And in the end, we can compute W, which is V minus R0, and prove knowledge of W instead of V and R separately. And this slightly transforms the equation, and although W is a bit larger than V, R can actually be super small. We can keep a hiding commitment under LWE while choosing R ternary, for example. So R will not affect the norm of V by much, which as a result reduces the witness dimension without increasing the proof modulus, basically. So we have better proof size in the end. Now, I said R should be super small so that it does not increase the norm and the proof modulus. There's quite a big margin between something ternary and the norm of a Gaussian preimage like V, okay? So the question then is, what if we take R to be larger? As long as it does not increase the norm of V by much, of course. Can this excess randomness be useful in some way? And the answer is yes. And this is what we called entropy recycling. The idea is to choose R in two parts. First, we have R sub hid, which is ternary as before, super small, and its only purpose is to keep a hiding commitment, as before. But then we also add another part, R sub mask, which we want to take as large as possible to mask the top part of V later on. And here the base K is just to lift R sub hid to the high bits so that these two components are well separated and do not interfere with each other. So what's new? Well, we keep everything as before with this new definition of R. And in the end, before the zero knowledge proof, we decompose V1 minus R in base K by essentially taking the Euclidean division with K so that WL is the remainder, the low part, and WH is the quotient, the high part. And what we're saying is that we can actually reveal WL in clear without breaking blindness and only prove knowledge of WH. Why is that? Because WL is basically the low part of V1 plus R sub mask, and all of that mod K. So if R sub mask is uniform mod K, then it perfectly hides the low part of V1, and WL can then be revealed safely without leaking any secret information on the partial signature V1. But what this allows us to do now is to only hide WH in the zero knowledge proof. And because WH is shorter than W by roughly a factor K, we gain a factor of K squared on the proof modulus, thus reducing the proof size. So now we have a more efficient blind signature scheme by leveraging this excess randomness injected in the issuance phase within the complete mechanism by masking parts of the partial signatures for free. We can actually push this idea further to hide the bottom part, V2, as well. For that, we use the exact same idea and use the full matrix, A sub t, as the commitment matrix. But this requires the user knowing t in advance, which is why we add a first round where the signer sends t. And the first round is very seamless. It does not involve maintaining any secret data on the signer side. It's very efficient, and yeah, so this first round is very transparent. Then everything is as before, except that we use A sub t for the commitment matrix. And also, because the commitment is already hiding for the first part of R, the bottom part of R that multiplies the rest of A sub t can be only some R sub mask without an extra hiding component. Then, in the end, we decompose the full vector, v minus r, possibly with two different bases, k for the top and bottom parts. But those details are in the paper. Now, although it makes our scheme 3-round, technically, it has a very different structure than Schnorr-like 3-round blind signatures, which were vulnerable to the Ross attack, for example, and we thus are not concerned by these attacks at all. So now we have our final scheme, but how does it compare to prior constructions? Well, previous works either relied on non-standard interactive assumptions like one more ISIS, which we want to avoid to keep a strong security base, or had fairly large sizes, or sacrificed the efficiency of the issuance proof by requiring general purpose NISC to prove symmetric primitives like shake evaluations, which takes around 20 seconds according to their own estimates. And in our case, we keep on standard assumptions and proofs of only algebraic relations, which are much more efficient, and we still reach competitive sizes of roughly 41 kilobytes. We can also improve on these sizes by replacing the gadget sampler with the recent truncated gadget sampler that we proposed with Olivier in another paper. It does not impact security at all, but it reduces the dimension of the gadget and thus the witness dimension, which improves the zero-knowledge proof component in particular. Finally, to showcase the efficiency of our issuance, we provided a non-optimized proof of concept implementation, which shows the full issuance can be done in about 1 second. And this is to be compared with the 20 seconds of general purpose NIST to prove shake evaluations, for example. We can still see that the bottleneck is the generation of Pi1 and Pi2, although Pi2 can be computed offline, as it takes roughly 90% of the issuance time. But because the proofs and the LNP framework only rely on arithmetic computation, we expect vast performance improvements with an optimized implementation. And this is all I wanted to present today regarding to this paper. So to wrap things up, we provided a new blind signature based on well-known lattice assumptions like modulo SIS and modulo WE. We have an efficient issuance process by only relying on proofs of algebraic relations. We reach competitive sizes thanks to our entropy recycling technique, which diminishes the impact of the zero-knowledge proof component. And although our scheme is technically 3 rounds, the first round does not involve maintaining any secret data and could actually be merged with prime messages in more complex protocols like eCache. So it's more like 2-ish rounds, okay? And in terms of perspective, I would say we now need to focus on the zero-knowledge part, either by finding new proof systems for lattice relations to reduce the size, or by having an optimized implementation for better timings. And that concludes my talk. Thank you for your attention, and I'd be happy to take any questions.
I guess that's it. I think we're going to lunch.